So let's try and see what is it trying to do. Well, you told me that x and y are two sets, and you have two one-to-one functions. This is injective as well as this is injective. So what do? You start off, go here, then you go back. This is not almost visible. So you go back, you come back, and so on. Now what happens? It could be that, so you start off with an x, then you take fx, then you take g of f of x, then you take f of g of f of x, and so on. Okay. Now, it could be that you started off with something such that this comes back to this. That doesn't stop this. Well, suppose if at the next step g of f of g of f of x, this becomes equal to, say, so it becomes equal to g of f of x. Say. Can this happen? Let us see. If this happens, since g is injective, it tells me that fg f of x is equal to f of x. Okay? Again, since f is injective, then it tells me that g of f of x is equal to this. So if such a thing, so this whole procedure therefore tells me that there are two kinds of points. So let me redraw these things. So let me redraw it. There are two kinds of schemes. One scheme looks like this. So one scheme looks like this. So you start here, go to something here, and you come back here. Okay? So these are one kind of points. All right? And the other kind of points are where this thing never ends. So you come here, you go back. You go back somewhere here, then you come back. And so on. It can continues. and so on. It continues. It never stops. So, these are the two kinds of points in X. So, the moment you see this, you immediately start saying, why do I not subdivide my X into this kind of points? These kinds of points, there is no problem. X goes to this and Y brings it back. So they are already in bijection. Right? The question is, how do I define the bijection here? That is the idea. So, now I am saying that this is the formal way now to do it. So how do I do it? Instead of taking a point, I now look into, remember this is the power set or the set of all subsets. So what do? I define a function. And how is this function defined? So I am trying to give you the picture. So I take a subset. So remember, I have this F and this G. So I take this subset P. I take it to its. Obviously, you know that P and GP are in bijective correspondence. Okay? That part is very well known to us. Now just look what I do. So, this part is in bijective correspondence. I'm sorry, this is F of P. So I first take P, look into Y minus F of P. Which is this part. And look at its image here. So this is this. So then look at its image here. So this part and this part are in one-to-one correspondence, right? And then I look into its complement. Okay? That's what I look into. So, this is my function. Is it clear? Is this function clear?
Yes, it is, Doc.
Stanley?
Not quite for me. The orange part, which is above F of P.
Yes.
The pre-image of it, I think, is that blank circle. Orange on X.
That's not the pre-image. That's the What I have taken this
Yes,
blank circle is the image
yes.
of this part under G. That's not the pre-image under F. So I'm always taking the images, not the pre-images.
Okay, I think that's where I missed it then.
Yeah.
Okay.
So first I take y minus f of p, and then I take its image under G, which is this part, and then I take the complement of that. Okay?
Okay. Now I get it now.
Okay. So now let us see. How does this look like? The way I have drawn, it seems that this is bigger. Okay, I don't know. It may also get smaller, I don't know. So the way I have drawn it, it seems as if this answer is bigger than P. Well, it depends on my F and G, but at least let us see something. Observe. What is the value of H at X? This is X minus G, Y minus F of X. Now, this is the image of X. Then this is smaller than X minus, well, this is your, now y minus f of x is actually smaller than y. So when you take it out from x, this is 1 to 1, right? So this gets bigger, right? So you see, and therefore this is bigger, h of x is bigger than this. On the other hand, if you take the empty set, this is x minus which is nothing else but okay. So you can see that, well, about this you cannot say much. Obviously this is a subset of x. H of x is obviously a subset of x, and this is, so H of the empty set is bigger than the empty set, and H of x is smaller than x. So you can see, now let's try and see what is happening. And why do I do this? The same idea that I gave over here, P and FP is in 1-to-1 correspondence. This part and this part is in 1-to-1 correspondence. So what is my idea in trying to do all of this? So this tells me that if you compare the values, so suppose you go like this, then you take a singleton set, then you take a 2-point set, and so on. You have a set in between and this. So you see over here, your H gives me a value bigger than this, and here it has changed to being a subset. So my question is this going like this? So my hunch is, from this, at the smallest end point it is bigger, at the largest end point it is smaller. So possibly somewhere in between it must be equal. So my idea is, so I'm going to take this difference h of p minus p. This set is getting smaller and smaller and smaller, and sometimes it becomes 0 and then it becomes kind of, so if you might, in sets we cannot do it, but you see what I'm trying to say, right? So so that's what, so the question is, does this happen? Now suppose if it happened, suppose if this happened, what does this mean? So this means that x minus this is equal to, so this means x minus p is equal to this. So what is the picture then like? The picture then in this case, if we had such a p, it says that it is like this. So you have a p, you have its fp, and this part is same as this part. And then we are done. Why? Why are we done? Because if I take an x, if I take a p from p, so how will I define? In this case I am done. I can now produce the bijection. How? Why? If I take an x from p, so I will take it to fx if x is in p. If x is not in p, it is something here, then there exists one unique point over here which is being brought by g to this point. So if x is not in p and so I take it to 1. Right? And then you should be able to say, so if I define this function as k, so remember now the last checking is remains, so k is actually defined as this set of ordered pairs, x fx, so that x is in p union x, y, x is not in p and okay. So k is this set, you have to show that is the required. Okay, so if I have such a, if I can come up with such a set, So the question is, is it really true? How do I how do I justify my intuition that, well, at the empty set I have h of the empty set larger, at the other end, which is x, I have h of x to be smaller, and then somewhere in between there must be so essentially the question therefore lies searching for fixed points of h. Why fixed point? That is a p which is a subset of x, such that hp is equal to p. So we have to search for that one. Okay. Now what do I do? Let me see. Suppose, so this is what I get from observation 1. Now let's have second observation. What happens, suppose, if we have p being a subset of q? How does hp and hq? Let's try and see. So, because you see, we are going to make our sets bigger and bigger and bigger. So, if this is true, then because f is an injection, this happens anyways, and the reverse happens because f is an injection. Okay, but then no, sorry, I made a mistake. Sorry. Yeah. Then y minus fq is smaller than y minus fp. And then g of this is smaller than, sorry, right? And then it follows that x minus so that means if p is smaller than q, then hp is smaller than hq. So now we are in a trouble. It seems so, but let's see. So hp is always increasing. So how can it become smaller? And that is where the magic starts. So what do I do? Take, say, A to be the set of all those subsets of x such that T is a subset of HT. Okay? Now obviously A is, so the empty set is there in A as we observe. So A is non-empty. Now let's see what happens. What do I suppose I take a t from A. Since t is a subset of ht, this tells me ht is a subset of h of t, right? Which I am writing as h square of t. So that's that business, what I was trying to do, those zigzags, right? So it satisfies, ht also satisfies the condition of inclusion in A, and hence if t is in A, then ht is also in A. Okay, so you don't go out of A by taking h. So you start from empty set, h of phi is still in there, h of phi is still there, h of phi, so and so on and on and on. So now the most natural thing is to take this union. So you take P to be the union of T of these things. The question is, where is P? So let's see. So the question to answer is, where is P? Now this is where that next lemma helps. H of P. This is H of this. But this is where it's a property of the image and unions. The image distributes over the union. So this is this. Okay. And then you know that this is ht. Since you are taking t in A, each ht is larger than t. So this is okay. But this you have already denoted is your P. So that is implying that P itself is a member of this. Okay? P itself is a member of this. And therefore, since P is a member of this, HP is also a member of this. That's what we did just now in observation 4. And hence, from the definition of P, HP is a subset of P. Therefore, AP is a fixed point, which then completes the proof. So, the idea is to find a fixed point of a certain function, and the reason starts from here. which again stems from here. And that completes the proof. Now, your comments, your problems on this proof. Obviously, I assumed lemma 7.4, which Stanley and Charles corroborated, saying that it was easy. So I didn't go into that, and that's obviously simple, lemma 7.4. It is just set theoretic manipulation which we have done already before. It's just a extension of similar things for finite unions and finite intersections which we did before. Okay, so now tell me, what do you think about this proof?
Is this one of those theorems that for now we can just use the results?
Yes.
And not necessarily have to understand the details of. I know eventually we need to understand the details of the proof, but for now, for me, it's still, I need to go through it again.
Yes.
For me, to internalize it. But I think I understand what the results of it is.
Correct.
Is it good enough?
Yeah. Sure. But what I will try to say again is look into the idea. This zigzag business tells you about this partition. Is that part clear? You start from any point x, then you can take fx, g of x, f of g, f g f x, and so on, right? This one, which I stated first, right? And in doing so, there are only two kinds of points of x. That is the first thing that one needs to understand. That points from where you start, so points where this sequence finishes off exactly here. So it's just a finite path. You go to fx and g brings you back. Okay? Now, these are one kind of points. For these points, obviously there is a bijection. This one goes to this and this one comes back. G brings it back. Right? The question is about points like this, where this sequence goes on and on and on and on. So what do you do? This from here, how do you tackle these sequences? The nitty-gritty of this is actually then hidden. So that is the transition. You need to slowly digest that this nitty-gritty of tackling these infinite, well, I don't know, these chains of, is done by this neat little apparatus. What do you do? Obviously, for any subset, its image and this under F, they are in bijective correspondence. So once you start with P, your thing of interest immediately comes to its complement, because this part is already in. So starting from a P, you go to its complement. So that's this. Now you have, with this part, that is in bijective, in one-to-one correspondence, since G is injective, to its image with this part. Okay? So once you take the image of this part, you come back to X, but that's not actually where you are really interested in. Why? Because this part is same as this. So what about the rest? So that's the interesting subset that should be considered. So P, you started off with a generic subset, and you should come to this interesting one. Once you start this, you plug in special values and you get hold of this. So that's how you start. So now the question is, so there is a strange thing over here. This is bigger, but this cannot be bigger. This has to be smaller because Hx is a subset of x. So somewhere, so the question is there, so think the similar thing about continuous functions. The analogy is here. So if you have an interval, closed and bounded interval, and if you have a continuous function which starts from below the x-axis and goes above, any continuous way to go, you must somewhere cut this. There must be a fixed point of this. So it is a similar idea that if you go from, in continuous functions, you go from below the x-axis and of a function defined over a closed and bounded interval, you go from below negative, so you go from a negative value to a positive value, or the other way around, from a positive value to a negative value. Somewhere you must cut it because you said it's continuous. So your idea is this kind of continuous? Well, I don't know. So the thing is, I'm at one end point it is bigger, and the other end point it is smaller. So the question naturally is it true that somewhere it is equal? Okay, and then you obviously, and what happens if it is equal? That's what happens if it is and that is what you want. You want this equality also. If it were equal, then you can present this bijection. You can produce this bijection. So now you have to search for this this fixed point, and that's where we start. We first show that it is monotonic. So that means if P is smaller than Q, then HP is smaller than HQ. So this is the first starting point. This result. Okay? And then you know that this is a typical case that you started off with. So you collect this. You collect all those subsets where H is bigger. Empty set is already there. And this fact helps you to give this fact. So this actually gives you a more concrete picture what is happening. So you start off with empty set, then it is the next one, then it is the next one, then it is the next one. Each time you are increasing it. Okay? Question is how long? How do I go? Well, the set theoretic idea of how long is, so obviously if you take this union of this and this is going to be the bigger one. So union of any along this finite chain, the union will be the last one. So why do I not take the union of all of them? So that means I take the union of all these members like this. And then the fact says, the search says therefore that P is in A. Now if P is in A, this one then tells you HP is also in A. So HP is bigger and it is also in A. But then but P is the union of everything in script A. So HP must be smaller than this. And that finally gives this. So these are the key points of this proof. Yes, I agree with Stanley that we have to use this idea and proceed to apply it again and again. It says roughly that if A is bigger than B and B is bigger than A, then A must be equal to B. So it says the idea of equipotence, or the idea of the set A is larger or having more elements and so on, is just like what we should think about it. So cantor schroeder bernstein theorem actually says that having more elements is, so this is something like our usual notion of an ordering, that if A is bigger than B and B is bigger than A, then A and B must be the same. So same over here means have the same number of elements. So that is what it says. Okay. So I said it again and we will apply it now. But before I go further, I want your comments, your problems or questions or whatever.
My question, Doc, in this area, to show equipotence of various numbers, the difficulty I have is coming with with an equation that you can show that there's a bijection. Like when you want to show that there's equipotence between integers and rational numbers, somehow you need to formulate an equation that you can show that it's both onto and
correct.
1, 2.
So let's try and use it.
Sometimes it's not an easy. In some cases, it's not an easy. Like now in the notes, I see you have an equation there, but in the other previous work that I've written, they actually draw all the rational numbers and then draw lines that goes diagonal and count those and say that it is countable, to show that the rational numbers are countable.
Well, that's an intuitive proof.
It can be equipotent to integers.
Yes, but that is an intuitive proof. That's not that Eratosthenes thief which you are saying you cut, or you're saying that the diagonal means you're saying the Cantor's diagonal principle that I did last time.
Yes, but for rational numbers.
Yeah, correct. Yes. Now here. Showing two sets whether they are equipotent or not in general. So the problem is in general. I give you two sets. You have to tell me whether they are equipotent or not, which one is bigger or which one is smaller, or what is their whether someone is finite and so on. These questions are in themselves pretty hard. And well, not for, well, this was obviously 400 years back. Mm, these about rationals and reals and so on, these were all hard problems. They have been solved. You will be you will be surprised to know that there are still some sets mm, whose mm, cardinalities have not been resolved. For instance, for instance, e to the power pi, right? A simple thing, even with numbers, even e to the power pi and pi to the power e. Both of them cannot be irrational. Which one is irrational? It boils down to finding some cardinality arguments, and it has not been found till yet. So you see, even such simple questions are still open. So I am not saying that, yes, on one hand, Schroeder-Bernstein theorem is the ultimate. That's the only way, or other ways based on Schroeder-Bernstein theorem to find out, to resolve this question. So in general, given two sets, whether they are equipotent or not, in itself is a very, very hard question. But for certain sets it might be trivial, for certain sets it might be more or less doable. In some cases it might be extremely difficult, in some cases it might be still open. You should not get puzzled or disheartened by this fact. There are certain sets for which their cardinalities or their exact cardinalities are even not known. They are not known whether they are equipotent to some other set or so on. So it is a tough question. So that's why I said we are now entering deeper waters, and for the first time you are going to see things which are very, very deep, difficult, but the key principle is Schroeder-Bernstein. And why is it key? So let's look into some applications of this, and which gives us some idea about how to use this. The first one that I said was naturals is equipotent with integers. Is this clear? So whenever we are having such thing, so remember the basic principle. You have to produce two one-to-one maps. Let me write one-to-one maps like this. Okay? If you have to show this thing, and then you can so this is equipotence, means you have to show this, or somehow you have to produce a bijection. So I am writing a bijection like this. So by this I am saying that when there is two such things in the arrowhead, it means it's a surjection. A tail like this, it means it's an injection, and both of them means a bijection. So any one of these are the three ways. They are equivalent, right? We just now know that they are equivalent. So these are the three principles or three tools that we have in our hand. Now let's see. So could you get hold of this first application? Even then, even going before this, let's do this. Where this is the set of even numbers. Could you settle this? This is the simplest.
Good evening, Doctor.
Yes?
Yes, we'll settle this because through the function.
Yes. What is the function?
F is equal to 2x.
Yes. Good. So here is the function, and that is the bijection. So f and this is a bijection, which is clear, right? So you can check. This is quite obvious. So this is the required bijection. So you have produced this. Okay? Good. So now about this, how will you do this one?
So I think there is a bijection because we'll look at the set of integers and rearrange it. Say, for example, 0 plus 1 minus 1 plus 2 minus 2. Can we do that?
Yes, but you'll have to give me the function. Yes, obviously, you can do that. 0 plus minus 1 plus minus 2 and so on. You have to give me the function. So, try it. Let's try. So, this is a school question. 1 plus minus 1. 2 plus 3 minus 3 and so on. So how is it coming?
So do we map it onto the natural numbers? 1, 2, 3, 4, 5, 6.
So you have to give me this function. So
The function.
again I'm using f, but okay, you know f in 1 and 2 are different. So you have to give me what is fn. which is in your school terms it says find the nth term, so that is Fn. Remember, we said that our natural numbers would start from 0. So natural numbers are 0, 1, 2, 3, 4, and so on.
Would we have a split function?
Yeah. Obviously.
Yeah, so we'll look at the not sure.
See.
Oh, is it good? Will be f of n will be n if n is a positive number, and then minus n if n is a negative number. Then what about 0?
Wait.
So,
There is no negative number in. There is no negative.
in the naturals.
Yes.
So if n is equal to 0, the first item that we can have will be 0.
Yeah.
And then the next place would be if n is equal to 1.
So you see here 0 is going to 0.
Yep.
1 is going to 1. 2 is going to minus 1. 3 is going to 2. 4 is going to minus 2. 5 is going to 3. 6 is going to so. Immediately I have it is n by 2 if n is even. Sorry, minus of n by 2 if n is even. Right?
Yep.
Now let's see about the others. So suppose, odds look like this. K equals to 0 puts me 1. 1 puts me 3. Right? So this is equal to, so here is the function therefore. Is this. Right? Or you can say it like this, n minus 1 by 2, so it is so this is actually n plus 1 by 2. You can also do it like this. Let's see. 1 plus 1 by 2 is this. 3 plus 1 by 2, 5 plus 1 by 2, and so on. So that works. So it seems it works. So now we have to check that this is a bijection. So that remains. That remains that you have to show that this is a bijection. It is immediate over here that the negatives are coming for evens and odds, they are all positives. Okay? So you have to show so take now there are two cases. X is less than 0 or x is greater than or equal to 0. If x is less than 0, if x is less than 0, then what is your scenario?
Even numbers.
Yes, so f of minus 2x is equal to x. Okay? That's the idea, right? And if x is greater than or equal to 0, f of 2x minus 1 is equal to x. So, for each x, there exists a unique, because you have given me the inverse actually, there exists a unique natural number. X is negative, so minus x is positive, 2 of x is a natural number, and x is greater than or equal to 0, so 2x is greater than or equal to 0. The only question is, the only point is over here whether 2x minus 1 can be, whether this can be negative, right? So that let's try and check. So this is less than or equal to 0 if and only if 2x is less than or equal to 1, which is only possible if x is less than or equal to half, which means because x is a integer, so that means x is 0, minus 1, minus 2, and so on, right? So that's the scenario. But the only possibility is over here for 0. That's the problem. So we have to make a change. So if x is greater than 0, so, and finally if x is equal to 0, then f of 0 is 0. So let's make this change. So with this check tells me that x is greater than 0. If x is greater than 0, then 2x minus 1 can never be less than or equal to 0. It's always positive, right? So therefore, you have exactly 3 cases. X is negative, x is positive, and x is 0. And in each case, you have produced this bijection. Okay? Produced the unique thing. For each x in z, you have, so in general, this check tells you, so for each x, there exists a unique y in N such that x is equal to fy, hence f is a bijection. Agreed? Questions, queries?
Agreed.
Others?
Yes, agreed.
Okay.
There's other functions that we can get that you can that gives the same sequence.
There can be several such sequences. You can, this is one such, okay? This is one such function which establishes this bijection. There can be several other functions. So let's see.
There's one that I know of. I was trying to remember it because it was one of the questions that we had to show. They've given us the function, you had to show that it's a bijection. And maybe if I give it to you, Doc, and it says Fn.
Okay, let's do Fn.
Fn equals to 1 plus in brackets minus 1 to the power n in brackets 2n minus 1 brackets 2n minus 1 over 4 divide by 4. No, the whole thing divide by 4.
Did I give you this?
No. It's when I was taking another
Okay.
class some time ago.
Okay, let's see. So this, you're saying that this is a function from n to z, right? Let's try and see what it is doing. 0. So this is minus 1 to the power 0 is 1. This is 0.
Minus 1 plus 1, 0.
Yes, so this is going to 0. This is 1. Going to this is 2 minus 1. That is 1. 1 minus 1. So this is again going to 0. Let's see what it is doing with 2. This is 4 minus 1. This is 3. 1 plus 3. This is 4. So this is going to 1. With 3, this is 5. 1 minus 5 is minus 4. So this is going to minus 1.
Minus 1.
This one. This is 7. So this is 8. Going to 2. 5. This is going to minus 2. So where you took, possibly they didn't have 0 in their domain. So their natural numbers possibly start off with 1.
From 1.
Yes. And this is also another function. Yes. Agreed. So, well,
the trick there was to show that it's a bijection.
Yeah, it's also a bijection. You have to prove that this is a bijection. Now, let's see. So let's see. This is going to be obviously a little more computation. So let's see, when is Fn greater than, equal to, or less than 0. So this means 1 plus minus 1 to the power n, 2n minus 1 by 4 is greater than, equal to, or less than 0. So this is the same thing as saying 1 plus minus 1 to the power n to n minus 1 is greater than, equal to, or less than 0. So this means minus 1 to the power n, so 2n minus 1 is greater than, equal to, or less than minus 1. So now you have to be a little more careful. No, doing this is going to be a little bit of a... yes, so from here you can immediately see that for n, so now for n odd, you need to find out 1 minus 2n minus 1 is this, which is the same thing as 2 minus 2n is this, which is same thing as saying 2 is this. So it is saying that 1, so that means, so that is, if n is odd, and less than or equal to 1, it is and if n is, so if n is greater than 1, then it is positive, right? So n is 3, 5, etc., positive. And n is greater than 1, it is negative, so it's negative. And n is equal to less than or equal, n is less than 1, that means n is odd, so there is no such case as less than 1, so the only possible case is 1, which is positive. So for odd integers, that's what we get. N is equal to 1 and it's no more positive, it is equal to 0. Okay. The other one is n is even. So this means 1 plus 2n minus 1 is this, which is the same thing as saying 2n is greater than or equal to or less than 0. It says n is greater than equal to or less than 0. So that means n is, cannot be less than or equal to 0. So for all evens, it is positive. And that's actually what I get. Okay? They are all positives. And now with this analysis, you take an x, choose and fix any x in z, and then you will, so it's just a change of, so you make x, you find n in terms of x. So x is this, you know n is negative, so it looks like this. If x is, again, x is this, x is positive, and x is 0. So I'm trying to find out 1 minus, x is negative, so here it must be this. So 1 minus 2n minus 1 by 4 must be x, and then you find out x in n in terms of x. If x is 0, you know n is 1, f of 1 is 0. And if x is, if x is 0, you know f of 1 is 0. And here again you have to do 2n is equal to x, so n is x by 2 and so on. So you know f of x by 2 is x. So and over here you have to do the same kind of a thing and come up with an answer. So that shows that it is. But it depends on the choice of your function. This function is also another bijection. So obviously, as I said, that this is this is what you get is, now you see, it just says that the equipotence says that there exists one bijection, there exists a bijection. It doesn't say a unique bijection, right? So therefore, you can find many answers. But what I wanted to say is something else. In this problem itself, you see these searching for this bijection and then finally coming up with a formula for it and then proving that it is a bijection, it obviously requires some bit of an explicit work and so on. But I would use CSB over here. How? From N, I know that there is this inclusion. Right? It's already there. Right? This is one-to-one. Correct? I have to produce another bijection. Another injective function. Okay. So what do? I take x to 2 to the power x if x is greater than or equal to 0, and 3 to the power minus x if x is less than 0. On the positives, it's a multiple of 2. On the negatives, it's a multiple of 3. Obviously, this is an injection. Right? And 2 to the power x and 3 to the power, these are injective functions. So, obviously, this is an injection. Why? Reason? 2 to the power x from naturals to naturals is an injection. And on negatives, the values are multiples of 3 on non-negatives, the values are multiples of 2. Multiples of 2. Exception is possibly at 0. There it is 1. It is never 1 at negative 1, right? So, therefore, no values are repeated, so this is an injection. So, CSB immediately tells me from this choice. Obviously, in place of f, you can take any. There is nothing special in 2 and 3. You can take any 2 distinct prime numbers. And that gives you. So, you see how quickly I decided without going in for that. And CSB, so the real muscle of the checking of the bijection, of establishing the bijection, then falls on it just falls on CSB. I don't have to. CSB tells me then there exists a bijection. Do you see the application now?
Yes, I do.
What about others?
Yeah, it's all right
You
though.
see it.
Yeah?
Yep, it's fine.
So you see, there are other ways, obviously, where you established the bijection either by this or by this. Well, that's fine. There's no problem in that. But now you see, this is another way. Okay. So now let's take another one. What about this? How do you do this? Answers?
Can we come up with a sequence of natural numbers that we put into one-to-one correspondence?
Yes, why not? Try. Give me that. So you have to give a correct. You have to give me a bijection. Right.
Okay, we start with 1.
Yeah.
Since because we are talking of natural numbers now.
Mm.
2, 3, 4, going on. And then on the second row, it's a square of 1, a square of 2, which is 4, a square of 3,
So one
which
minute,
is
one
9,
minute, one minute, one minute.
and so on.
So what are you doing?
1, 2, 3, 4, and so on.
Okay.
And then on the second row,
Mm.
we have got 1,
Mm.
which is 4, which is a square of that one, 9, and 16.
But I'm saying, I'm just indicating these are the repeats. What will be your third layer? 1. Do you want to say something like this?
On that part, I'm worried because now that's now a cube here. I'm not sure where the cube is coming from.
No, I thought you were going to say cubes. But even then, you see, even if you don't have this, there is a repetition.
So if it is a repetition, it means it's not injective.
Yeah. So roughly the idea is that you have this infinite box. And so on. Right? So these infinite blank spaces in yellow, you have to fill in all the natural numbers, but you can use them only once. That's the whole idea. There should not be any repetition. If you can do that, that means that you have given me, because this is, you will say 0, 0, 0, 1, 0, 2, 0, 3, 0, 4 and so on. This is 1, 0, 1, 1, 1, 2 and so on, and this is 2, 0, 2, 1 and so on. So then you will have given me a bijection from n cross n to n, whose inverse you have given. Yeah, so you either give me this or you have to give me this. Any way round. It's like an infinite Sudoku, and with infinite choices. Okay, but remember, as I told you before, you have three bows in your, three kinds of bows in your quiver. Either produce me this, or produce me this, which is CSB, or somehow else, by some other technique, produce me this. You know, equipotence is, say, suppose if you can show that there is a third set to which A is equipotent and B is equipotent to a fourth set, and the third and the fourth sets are equipotent, then you have this to be equipotent. So if you seem to be despaired with this one kind of arrows, you have to start using the other kind of arrows. Any idea?
Doctor, can we use your grid and do the zigzag?
That means CSB.
Yes.
Yes, good. Try.
The yellow.
Yeah, try. So you give two one-to-one functions, one f from n into n cross n, and another g from n cross n to n. Yes, that's also acceptable. So instead of bijection, you are now trying to give me this. So, do you have a candidate for f?
So it is going to be f of n.
Yeah.
Function. And it is going to have to map onto a pair.
Yeah.
which means we can have that. So for the first coordinate,
Yes.
can we have something, and for the second coordinate something?
Yes.
This is, I suppose it's again going to be this odd and even story. 2n and 2n plus 1 or 2n minus 1 for the second coordinate.
Okay. Okay, so let's try. The only problem with 2n minus 1 is it at 0 it will be negative, so let's put it at 2n plus 1.
Plus.
Okay. Now, obviously this is bijective, because if 2n and 2n plus 1 is, I mean to say injective, this is equal to 2m and 2m plus 1, then obviously 2n is equal to 2m, so this means m is equal to n. So this is one candidate. Correct. Correct. So this is a bijection, the injection. What about G?
Can we take it the sum or
Okay,
m
sum.
plus n?
Let's see, sum. But I know 1 plus 3 is equal to 3 plus 1 is equal to 2 plus 2. So G13 is equal to G31 is equal to G22. Sum doesn't
Which is
work.
not injective.
Similarly, 1 times 3 times will also not work. Or if you take 1 times 4, so again times will not work. So we have to think about something else.
Two to the power m n.
Good. 2 to the power m, and then if you take just this, then the problem is, since there is no n business, so G m, if you fixed n, this is equal to GM2 and so on. So somehow you have to also bring in n. So how do you bring that?
Would we be able to multiply the two? Let's have the mn.
Again, if you put mn, 2 to the power mn,
You have 1 4
is equal to 4 1.
and 4, yeah, okay.
How about n times 2 to the m?
Okay. If you take this, let's see. So then let's see, 2 to the power 2 times 3, this is 4 into 3, this is 2 into 6. So G 2 3 is equal to G16. So here your thing was that didn't work, addition doesn't work, this one also doesn't work. Next level, next thing.
Just using the other example that Doctor gave us, so I'll say 2 to the power n, multiply that by 3 to the power n.
Good. Times. So suppose at 0, 0, now this is 1, since m and n are all integers. Okay? Right? There's no other way. The moment m and n is positive, there is a multiple of 2 on one side, so it cannot be 1. Right? Okay. Now suppose 2 to the power m times 3 to the power n is equal to 2 to the power m prime times 3 to the power n prime. So little bit of school algebra tells me this tells me m minus n prime. So this tells me m is equal to m and n is equal to n. So this is one such. Correct. Correct. So you see CSB with a little bit of a tinkering tells you. Okay, this is fine. Now with here I have an even much more simpler example of Fn. Take Fn to be n0. I have only one argument. I have to make it, so I fix the second coordinate at 0. And obviously this is 1 to 1. So you see, so what are you doing? So if this is 0, 0, 0, 1, 0, so you're just picking up this. So this is the copy of n already inside it. So you see, this is something, if you have any set x and you have any other set y, and y the only thing is non-empty, and you choose a point from y, this map is always 1 to 1. Right? So the idea is, if this was your x side and this was your y side, you only needed, this is non-empty, so that you needed a point over here. What you are taking is nothing else but this line. through y naught. This line through y naught. That's what we are taking. So you see, there are so many, for each y over here, there are copies of x sitting inside x cross y. Similarly, for each fixed x naught, y is sitting inside your x cross y. So you see, this is a very nice idea to utilize. So you see, this gives you a very quickly one side and the other side comes up. Okay, so now let's again have another application. How do you do this?
Can we again use a fixed point?
This same CSB you meant to say, right?
Yes.
Yes, you can. Yes, you can. You see, there are three ways, as I have said.
Mhm.
Either somehow produce a bijection, that is this one, or this one, produce two injections, which is CSB, or find out from somewhere you have already obtained that A is, so by this I meant that you have already obtained this and you have already obtained this. So you have already assured that A is equipotent with C, B is equipotent with D, and C is equipotent with D. So these three equalities have been already obtained somehow. And then therefore immediately you conclude, because this is just composition. How does this happen? C is equipotent with D, so you have a bijection. A is equipotent with C, so you have a bijection. D is equipotent with B, so you have a bijection. So you now compose, and that gives you a bijection. So that happens. So you see, so somehow you have these three things already established, and then you so there are three ways: either use CSB, or somehow come up with this bijection, or use previous information to do this. Okay, so these are the three techniques. So now let's see about this.
Can we use that technique of the third one, because we know that n is
Yeah? N is equipotent with N cross N.
We, yes, and then G, and then and N is equipotent with Z.
Correct?
So
So correct. So yes, you have, sorry. So you have already this. You have this and you have this.
yes.
Good. Now about the third one.
So now do we need to just show that Z cross Z is equals, it's equipotent to N cross N?
Yes.
Z is equipotent to natural numbers,
Yes.
and Z is equipotent to Z cross Z, and N equipotent to this. So why can't N be equipotent to Z by Z? It's not.
No. There's a small line missing, and that is, I leave you with this observation. Suppose if F and G then and why is it so? What's the proof? Proof is immediate. Remember, what is, so F is this, so F is a bijection. So you have its inverse, right?
Yes.
G is a bijection. So you have the inverse. Now remember, so you have this F, sorry, so you have this F cross G, that is the unique map, right? And you told me that you have it's a bijection, so you have this. So you have this unique map. right? And hence, therefore, F cross G, or we also did something similar. F cross F inverse is identity of B cross identity of D, which is identity of D cross D, and similarly. So therefore, F cross G inverse is F inverse cross G inverse. So F cross G is a bijection between. Alright? Okay? So in particular it says if A and B are equipotent, C and D are equipotent, then A cross C is equipotent to. So this means that is so therefore, since N is equipotent to Z, you have this third equality by this. And hence Z is, so you're done. And hence, I'll just leave you with this, and hence you have, now you are going to use induction. N cross N, remember it is nothing else but the set of all functions from two element set to N. You get it now? So you've seen how things are now for me. Yeah? I leave it to you for you to complete the proof of this observation as well as number 5. So you see now how this equipotence business is coming.
Yes.
Okay. Queries, questions? Do you feel a little more comfortable now, Stanley?
I think it's much better than at the beginning. But I still need some more work to go through the lecture again to get more comfortable with it. But now I have a clear idea on how to approach it.
Yes.
I wasn't aware of the 3 methods on how to use either the bijection or the cantor, schroeder, bernstein, and the last one that we did. So I wasn't aware that you could actually approach it in 3 different ways. Yeah. Okay, thanks, Doc.
Thank you. If there
Thank you, Doc. Thank you. Good night.
Thank you. Keep well.
Thank you, Dr. Parsa.
Bye, everyone.
Bye. Keep well. Good night.
Bye-bye.
Bye.